In this sixth video for our course, I'd like to talk a little bit about calculations with vectors in a kind of general sense, and then in follow-up videos and in class we will talk more specifically about how these types of calculations should apply to the types of physics that we're learning about in this course. So I'd like to start by noting that two different vectors could be equal to one another. For example, as we says here on the page, vector A could equal vector B. In order for this to be true, that means that vector A and vector B must have equal x components and equal y components and equal z components in the same coordinate space. So that shouldn't, I think, be very surprising, but we want to make sure that we start out with that as an explicit statement, that two vectors can be exactly equal, even if they're in two different places. The second thing I'd like to get into is how to add vectors. And the way we add vectors is there's a mathematical way and a visual way, and they have to mean the same thing, of course. Adding two vectors together mathematically means adding together their x components, and then adding together their y components, and then adding together their z components, keeping in mind that vectors can have negative components. So a positive x component in the a vector and a positive component in the b vector would add together to give a bigger positive component. But a, say, positive y component in the a vector and a negative y component in the b vector would add together potentially to 0 or possibly to a negative sum. So you'll want to be careful about your negatives. Visually, what that means when you add together vector A and vector B to give you a, for example, vector D as the sum, this will show us visually in two dimensions. Vector A is our red vector, and in order to add our vector B to it, we would visually represent that by drawing vector B starting from the end of vector A. As I mentioned in the previous video, this is more obvious when you're talking about things like displacements, because first you walk this distance and then you walk that distance. And so in order to treat those as vectors, you still have the sequence of first this, then that. This is less obvious with certain other types of vectors, like the example with the velocities that are happening simultaneously. In the previous video we had the boat in the river experiencing simultaneous velocities. To show visually how to add those two simultaneous vectors, you still represent them like this, tail to tip method. And then the resultant vector is starting at the origin of the first vector and extending to the tip of the second vector. And you could add 3 or 4 or 5 vectors together like this. Your textbook actually shows that a little bit. The way we take this visual representation and turn it into a mathematical calculation is, let me take vector D out of there visually. I would go back and start an origin and say, this is the direction of x horizontally, and this is the direction of y vertically, and now I have an origin and I have a coordinate system. My vector A has a x component and a y component, and I would want to establish exactly how much each of those are. And if I'm not given that information, I would find a way to find that information, perhaps having to go through some trigonometry to determine it. Vector B also has an x component and a y component that are not measured from the coordinate system origin, but from vector B's origin. So you can see here vector B goes this far in the x direction and this far in the y direction. And now let me take them over to the side of the screen here and say A in the x direction plus B in the x direction is this. A in the x direction plus B in the x direction gives me the x component of vector D. The same thing in the y. A in the y direction is this downward pointing red arrow, and B in the y direction is this upward pointing blue arrow. And when I add them together, I get this resultant that goes from the origin of the first to the tip of the second. So my D vector, the resultant vector of A and B, has a x component that is this dotted line and a y component that is this dotted line, each of which is found by adding the respective components of the vectors that are being added together. So A in the x plus B in the x gives me this green dotted line. A in the y plus B in the y gives me this green dotted line. And numerically, that is exactly how I would go through with actual values to each of these components to determine the resultant vector. So visually, that's what it looks like. mathematically, that's how we do it. If that's not entirely clear, then I suspect some examples would go a long way to helping clear that up. Your textbook has some examples that they walk through in terms of what they call the parallelogram method. And the key point to the parallelogram method of vector addition is to note that if you have two vectors that are given like this, A and B, they're not drawn from a common origin, and they're not drawn tail to tip initially. So one is just from here to here, and the other is just from here to here. What do you do with them? You start them at the same origin and draw vector A this way and vector B this way. You're allowed to move a vector from one place to another in order to manipulate it mathematically. Because we said that two vectors in two different places can have the exact same physical meaning. So if you take vector B from here and move it up to here without spinning it around or stretching it, it doesn't change meaning. And that's how you would go about moving them to where you need them to be for calculations. I'd like to point something out about vector subtraction. I don't foresee doing a lot of vector subtraction, but when it comes up, I want to point out that subtraction is addition. So if you're asked to take vector A and subtract vector B in order to find the difference, vector D, that can be rearranged a little bit to say, well, vector D plus B gives you vector A. You could also rearrange it to say, if A minus B gives you vector D, then A plus negative B gives you vector D. And in this case, it's important to know that vector negative B is the exact same magnitude as the vector B, just in the exact opposite direction. So that can be really useful, as we'll see here visually. If I'm taking vector A, which might be this vector, and they're asking me to subtract vector B, which might be that vector. Visually, subtracting that blue vector from that red vector might seem problematic because they're not even in the same direction. How do I subtract one from the other? And the answer is I take away vector B and instead put in a vector negative B. I know how to add vector A to vector negative B. Now this is just a tail to tip vector addition. So I'll move vector negative B to the tip of vector A, and the resultant vector D will be from the origin of A to the tip of vector negative B. That is vector A minus vector B gives me vector D. And again, mathematically, it is laid out here as vector D is equal to the x component of vector A plus the negative x component of vector B in the x direction. And then in the y direction, it is the y component of vector A plus the negative of the y component of vector B. If you are ever asked to multiply a vector by some scalar value, then that just means multiplying it by some number. And you just multiply each of the components of the vector by that number. Again, I think that would be something that would be useful to see in practice, so we'll make sure to do that in some examples. Visually, it just looks like this. If I have a vector A, and it's this red vector that's on the screen, 4 times A literally means A 4 times. And when we add vector A to vector A to vector A to vector A, we're adding them tail to tip the entire time. That also means that the x component of A and the y component of A are each being multiplied by 4. So you are multiplying the x component by 4 and the y component by 4 to get a resultant vector D that was equal to 4 times the vector A. I'd also like to mention really quickly that we're going to make use of unit vectors. Unit vectors are vectors whose magnitude is 1 and their only purpose really is to designate a direction. So we will use those as our way of designating a direction when we are reporting the magnitudes of some vector that we're working with. So as it says here, to describe a vector in 2 dimensions, or in this case 3 dimensions, Cartesian coordinates, we would say vector A is equal to ax magnitude, and then we would write x hat, and then a y magnitude we would write y hat, and a z magnitude, we would write z hat. The z components of it would just not appear if we were talking about two-dimensional vectors in a two-dimensional plane. And I think this would make more sense, again, if we saw some actual numbers being used. So let's make sure that we do that in class. I do want to note also that the x hat, y hat, z hat unit vectors are often instead reported as I hat, j hat, and k hat. I'm not really sure why one is preferred over the other. They mean the same thing. X hat and I hat are just different ways of saying the same unit vector, which really means in the x direction. That's what it represents. And then j hat means the same thing as y hat. Z hat means the same thing as k hat. And so any given vector in three-dimensional space can be reported as the components in the x and y and z directions. Okay, those are some of the mathematical tools we will use to work with vectors, and we'll make sure to use them in class this week and next week to really emphasize what it is that they mean. So I look forward to that.